All right. Good morning. Good morning. Let's wait for everybody to come in. I don't know if this is the best angle, and I know the screen's bright. I'll have to work on that for tomorrow with the brightness. But I think this is probably the best angle. We got about a 5-second delay, which I cut down from 20. Move it there. Pretty good. Schoology is down. Schoology is down. So hopefully everybody has their subscriptions and can get in the right way. We're just going to give it a minute or two to let people come in. Next time we'll try to start as close to 8:30 as we can. So good morning, everybody. Just so it doesn't get out of control here, let's try to keep comments to a minimum for questions once I start. You guys are welcome to check in now, and then once I start teaching in about a minute or two, then you're going to want to cut the comments just so I can see questions. I think when I back my head away, you can see the screen a little bit better behind. So I'll try to remember to keep my head back a bit, then the screen's a little clearer. Is the screen too small for you to see? Okay. What about when I draw it on the board? Like that. Too small to see? Does it feel like it's too far away? The board is fine. Okay, well, I'm going to use the computer for just to get the ideas that I want you all to have. But I guess you guys will focus in on this board then. And maybe we can get a better angle for this board then. Let's see. No, that's a light. I'm getting a light in there. Let's angle it so that that's not the case. Right up in there like that. Let's see how that goes. How's that? Okay, if the screen is bright and we're not going to use that, then I can just back that up. Just back that up. Okay. Well, don't worry about the screen. Let's worry about what's on this whiteboard, and I'll get you the ideas. Yeah, I know it's bright. Let's see. Well, I guess I can go to this one and shut this one off. Okay. Then the light, I don't know, then the lighting gets a little. All right, we'll work this out, folks. Just be patient. We'll get better at this each time we do it. Okay, we tried the lighting change. I'm going to put the light back on. Just give me a sec. Okay, try that. Okay, it's a glare, good then. No, it's the camera glare. That's also too bright, not the actual computer brightness. Just close the laptop when not needed. I'm not going to keep closing the laptop. I got to look at it for the ideas. I can turn it away though. All right, here we go. Slightly better. All right, and then let's angle that more towards the board. I got the board really close to the camera. I need a webcam, I think. You don't need the laptop, folks. You don't need it. Just we're gonna go off of the board. Okay? All right. Let's cut down comments unless you just absolutely cannot see. If you do have a question, let's go ahead and use this chat to ask the questions only, and let's cut out everything else. All right, and you guys can talk to me on Schoology after with any input you have, suggestions, things like that. I'm not going to turn on slow mode for comments either. I'm just going to leave it as is. You guys just ask questions on a needs basis. All right, so we're going to go ahead and get started. It's 8:36, so we'll go for about an hour until there's a good stopping point around the hour mark. All right, so here we go. So we are getting into chapter 11. Most of you have enough background from 10 to do this, so we're going to be using what we learned about area. So let's talk about, we want to open up this next chapter on volume and surface area with, what that's all about. So we're just basically kicking things up a dimension from last chapter. We did 1/2 AP, right? So we had 1/2 apothem times perimeter. That got us the area of regular polygons. We had 1/2 D1, D2. Remember what that's for? Kites and what? You can respond. Rhombuses, right? Kites and rhombuses. Okay, that's it. Rhombi, I like that. Okay, so, and we had other formulas that you're going to have to carry on. The average base times height for the trapezoid, base times height for your rectangles and parallelograms. You're going to need your trigonometry because we're going to be still finding those areas. All right, so of course, why is this important? Because when we're going to study the sciences, especially the physics, the real world is not two-dimensional. So we're going to have to scale everything up a dimension or two. All right, so I think you're well prepped for that. Let's get started. First, let's talk about what this is. That's a point. How many dimensions does that have? 0. Okay, so with no dimensions, it doesn't take up any mass. It's just a point. It's a location in space. All right, so it has no dimensions. So in order to get another dimension, we need the next dimension to be at a right angle to that. Well, how do you get to a right angle to a point? It doesn't seem to have sides or anything. So it looks like we have maximum flexibility here. We can come in, anything is a right angle, you could think of it that way, which is an interesting way to see that. So if we add another dimension, I want you guys to think of this as I'm going to pull this point and stretch the point in a certain direction, a certain amount. So I guess you could say along a vector. So let's say that I take a point and I stretch it out. Okay, so I could keep going forever in both directions, so we can make a line out of that. All right, and it's interesting that it's now we have one dimension, but it goes two directions. All right, so these are going to be representative of the edges of our polyhedrons, which is a word you need to know. Polygon. Now we're moving to polyhedrons. All right, so the edges of our polyhedrons are going to be made of these single dimensions. So I forgot to mention that for the points, these are going to be the vertices. All right, so like I said, I want you to start with the 0 dimension and think of it as stretching it into a, did I smell? Oh, yeah, thank you. I did spell it wrong. Sorry, another error I have to fix for next time. I'm not used to this board. I miss my smart board already. Anyway, let's get back to this, okay? So we stretch the 0 into 1 dimension, all right? And then, okay, so now let's move to the next dimension. So there you have your vertices, your edges. What else do we have with 3-dimensional shapes? Well, I want you to think of this as it's bright outside, there's a window right here, and we're going to pull down the shades. Notice that that direction is perpendicular to the one that we have there. We have 1 dimension. By the way, moving along a dimension, that's another thing to think about as we go along this chapter. Moving along a dimension, it's forwards, positive, backwards, negative, right? So that direction that we get, you can have negatives going that way, positives going that way, and you're still moving along that dimension. Now, let's go to the next dimension. So 2 dimensions. 2 dimensions, we're going to pull this down like blinds. So what is that going to do? This is going to all go down. Every point along here is going to go down along the same vector path. Okay, the same distance, the same direction. Okay, and they're all perpendicular. And you think of that, and then you get this. You get a plane. All right, so now we have 2 dimensions, and these for our 3-dimensional objects, does anybody know what those are going to be? That's a rectangle, yes. But if we had vertices and we had edges, if this was a part of a 3-dimensional object, what's that going to be? It's going to be this. We're going to call those faces. Those are going to be faces. Good, 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 good. All right, so now we have 2 dimensions. Just like you see on we can graph this on a coordinate plane. It's 2-dimensional. Now, how on earth I think you already know, how am I going to, don't spam it, please. All right, I'm not going to use names, but you need to stop spamming. I said only for questions. If you want to respond once, okay? All right, so how on earth am I going to get a 3rd dimension here? All right, so we're going to take the face. Now we need to go perpendicular to that. Every point on there is going to come perpendicular to that. And you can see what I'm doing with my marker. It's going to come right out like that. And that's going to be perpendicular. And every point that you could think of. Now there's an infinite amount of points on here, right? Everywhere, even on the edges, right? If they all come out along the same vector pathway, they're coming out along that 3rd dimension there, okay? And then we're going to, now I can't do this for you. You're going to have to imagine now. Let's go to your imaginations. We're going to pull this out, and then this shape that you're seeing, this face, is going to stretch out. So you can almost think of it as, here's more of these boards that I have, starting off with, 1, and stacking them basically towards you, right? And if you want to see the thickness, you're creating thickness by doing that if you look at it from the side, okay? So, and you can keep stacking them, and that gives you, maybe you want to think about it, if you had a base or a length and a width, maybe now you're getting a height to it, okay? So maybe that's how you want to think about that, all right? All right. All right, so let's move on. So these are going to be the parts of our polyhedron. So if we're going to make a polyhedron, I'll just make one for you. Most of you know how to make them. By the way, before I draw, while I'm drawing the polyhedron, what would be the next? How would you get to a right angle to space? How would you do that to get a 4th dimension? Most of you know what that 4th dimension is already. Okay, what you can do here is you can overlap them. That's one easy way to make one of these. Okay, you have your vertices, no dimensions. You have single dimension. Those are your edges. You have your faces. And then you have maybe a base down here, base 1, and a second base where you took that and you stretched it up. Okay, so 3 dimensions. Now, how on earth would I get to be perpendicular to every point, not just on one face, but inside and all of that? How am I perpendicular? This is, difficult to think about. How am I going to be perpendicular to all of that? I was having some thoughts before today. I was thinking about that. I go back to the point, and I'm not sure about this, but these are my thoughts. With the point, how did we get at a right angle to that? It felt like we had flexibility. So maybe for this object, maybe you want to think of it as a sphere instead. Right? Imagine that that's a point that's, infinitesimally small, and you could be at a right angle to any of it, and maybe that's what time is doing. I don't know. That's above my pay grade there. So, but anyway, let's move forward. Let's get on into our chapter on the 3 dimensions. All right, so I'm going to go to the next slide now. Bear with me. All right. So, some of you already got a preview of this. We're going to talk about the Swiss mathematician Leonhard Euler. All right, or Euler. Okay, let's get rid of this. I think it's easier just to keep using the same board. So, Euler, spelled like this. I'm going to spell that right. Swiss mathematician discovered a relationship among the number of faces, vertices, and edges of any polyhedron. Any polyhedron. Okay, so even ones you really can't imagine because it has so many vertices, edges, and faces, and they can look quite different. Looks like somebody's saying discovered a relationship among. Oh, you're typing up what it says. No need to do that. Let's not. Why are we typing those things in there? Let's not type those things. I see. Some of you are putting out, going ahead. Let me just say that again. Let's go back, and the rule is going to be don't spam the site with stuff. It's actually not helpful. I know some of you are actually trying to be helpful, but let's not spam it that way. Okay, so hold off until you actually have a question, and I'm going to wait until that stops. So let's stop spamming it. Okay, thank you. All right, so let's go ahead and let's look at the next slide. Oh, before we do that, let's do a little experiment. Some of you already know, but if you actually do an easy one, let's start with the one that we all know, like a cube. And let's just count those things up. Okay, so let's count faces, edges. Let's do it like this way. Faces, edges, and vertices. Edges, vertices. Okay, faces, it's like a number cube. It's got 6. Edges, we can count them. Let's see, we have 1, 2, 3, 4. And in the back, you have 1, 2, 3, 4. That's 8. And then the connectors, okay, 9, 10, 11, 12. Okay, vertices, 1, 2, 3, 4, 5, 6, 7, 8. Looks like we have 8. Okay, so you're going to always have more edges than faces and vertices as far as I can tell. But there's probably a relationship between them that some of you already know, and we don't want to give that away. We want some discovery. So part of the way we're going to have to do this is to allow for students to discover. And if you guys are typing in, going ahead of things, you're going to take away that ability for people to discover. Okay, so what if the base I want you guys to start looking at it as base 1, base 2. If it's a pyramid, it will only have one base. Okay, but what if, yeah, let's use a pyramid. Same type of base, rectangular base, except when it stretches, all these points converge into a point. Okay, so let's say that's the point that they converge into. Okay, so then now let's count up these things. So how many faces is it going to have now? It's going to have the base, the front triangle, the back triangle, the one on the right, the one on the left. It's going to have 5. Edges, you're going to have the 1, 2, 3, 4 on the base, and you're going to have 5, 6, 7, 8. Okay, and then vertices, you're just going to have 1, 2, 3, 4, and 5. Okay. Now is when you want to look at the pattern of what you see. Now, what people already put on there, if you read up, you'll see that, let's see. Oh, I think the formula is face. Yeah, that's what I'm talking about, is we don't want to say what the formula is. We're trying to discover the formula. I know a lot of you, I think with 2 of my classes, we already talked about this. So there's a little bit of glare on the board there. Try to get rid of that. Okay, so if you look here, see if you could find a pattern here. And now that everybody said it, we can just talk about it. If you notice that if you take the edges, 12, and you were to add 2 to that, it would be equal to adding those 2. And let's see if that works for the pyramid. If we take the edges of the pyramid and we add 2, it should be the sum of the other 2, and it is. Okay, and so that's, one of Euler's formulas that he came up with. All right, so the formula is going to be, that's going to be on the next page, just like what everybody said. It is going to be, I'm going to just get another board now. Just like you said, if you take the amount of edges and you add 2, that's going to equal to faces plus vertices. So I'm going to give you guys a problem. I'm going to give you a polyhedron. You ready for your first problem? Let's say that a polyhedron has 102 edges, and it has something that would be very difficult to see. Let's say 43 vertices. How many faces does it have? You can type your answer in if you'd like. I'll give you a second to do that. Nobody yet? Anybody going to type that in? I got a couple different answers there. Ooh, we have a disagreement. And let's keep it, let's not be silly about this, which it looks like you guys are doing a good job with that. All right, and let's cut it off there. If you haven't answered already, let's cut off your answers. And let's take a look at it. It looks like we have some disagreement there. So let's cut those answers now. If you feel you need to put the number there, then that's fine. If you feel you need to be heard, that's fine. But it is going to spam this up. So hopefully you guys don't need to keep putting the number. It looks like most people are getting 61. So let's see. Number of edges, 102 plus 2. Vertices, we have 43. And then it's just a simple one to solve. This plus the faces needs to add up to 104. And you would need to add what? 61. So this would have to be 61 so that this would add up to 104. And that's basically why Euler's formula helps us so much, is because you're not always dealing with a polyhedron that's easy to work with. Okay? All right. So let's get another slide. Let's get a fresh one here. And let's move on. So let us, on your test when we come back, you are going to have to know how to make a net, but we'll get to that in a second. Okay, so let me draw an object. Actually, I'm going to skip that one. Let's go to the next slide. Okay, so let's see if everybody on your own paper, hopefully you guys brought paper, can you draw the net for these objects? Let's do maybe 3 of them. So let's start easy. Rectangular prism. And then let's do the 2 that students mix up. Let's do triangular prism. And then let's do 4. Let's do rectangular. I'm going to do shorthand prism, pyramid. And we'll do a triangular pyramid. Now, if you don't know what a net is, we'll go over these in just a second. So go ahead and take 2 minutes and see if you can quickly make a net. You're basically taking the 3-dimensional object. First of all, you might want to see if you could draw a 3-dimensional object. Not everybody, it doesn't come easy to everybody. See if you can draw the original 3D on your paper, and then take it down and imagine cutting along the edges so that it flattens like a cardboard box. If you wanted to flatten a cardboard box and set it on the table or on the ground, what would it look like? And so you're going to have to capture all of those faces and where and how they're attached. So go ahead and take 2 minutes. Go. Yeah, I'm seeing here, you guys, if you're using this not appropriately, I'm not going to keep warning. I'm just going to have to remove you from it, and you'll have to catch the video later. And I might just have to set an example by actually doing that. So please be responsible with this. Only put appropriate messages in. Don't tell people to be quiet. Don't just leave it, okay? I'll take care of that. All you need to do is go ahead and do these problems, and you know, and then if somebody is doing inappropriate things, I just have to start removing people. Okay, I'm gonna do on another slide here. I'm going to do a rectangular prism. While you're doing it, I'm going to do it too. So right, and then you are going to have 1 or 2 nets that you're going to have to do on the test when we come back. Okay, so just going to take this out for a second. I'll put it right back. Now there are different ways to do this. If you want to be creative, I know some of you like to do this in a creative way. You can move this one over here if you want. It doesn't have to be across from the other one. Okay, but that's probably the easiest one, rectangular prism. And I probably will not have a rectangular prism as the net. It's probably going to be triangular prism or triangular pyramid or rectangular pyramid. Okay. I'm going to take that one off just so now you have an idea. You can start doing these here. Okay. All right, I'm going to do number 2. First of all, try to draw it. There's my triangular prism. Dotted lines are in the back. So, but you can see that there's a base down here, and we stretched it to the top. And those are, by the way, that's like a congruency transformation or an isometry or a rigid motion. Okay. So you have to make sure all those pieces are there. And in a prism, you should notice that the top and the bottom, although they are triangles, all what we call the lateral, the ones that go around them, all the lateral faces are rectangles. And that's true of, you might want to listen to this, that's true of all prisms, that the lateral faces have to be, no matter what the shape the base is, all of those have to be rectangles. And you're going to see in a pyramid it's not, and that could help you a lot when you're doing this. Okay, so let me draw the net. So I'm going to capture all three of those rectangles first, and then my two bases. Something like that. Not exactly, but that would work. Okay, so take a look at that. All right, little spaceship there. All right, so you can see here are the two bases. There's a base, there's a base, and these are all lateral bases. They have to be rectangles. And they were in the rectangular one. Here's a base, here's a base, and these are your lateral bases. Okay, they're always going to be rectangles if there are two bases, and if there are two bases, it's going to be a prism. Okay, so we're only going to be studying prisms and pyramids, so it's going to stay simple this chapter. Okay, all right, let's do the next one. Now, the next one gets mixed up with number 2, the rectangular pyramid. So let's see how we do on that one. Rectangular pyramid, that one should be easy. That's the pyramids in Egypt. Okay, this one has one base. That's what it's going to make. That's what's going to differentiate it between the prism and the pyramid, is that when you're trying to stretch it up the next dimension, all these points don't go straight up. They converge on a point. It's almost like that other base collapsed, like a singularity almost, into a point. Okay, so that's going to give you a pyramid, and that's going to have all sorts of implications that we're going to talk about later. Okay, so if you notice, in a pyramid, notice all these faces have changed. They're not rectangles anymore. What are they? Just one or two people can answer. Whoever the first couple are can answer that. Yeah, yeah. They're all going to be triangles. So that's how you're going to be able to tell if you're not rushing on the test. That's how you're going to be able to tell between a pyramid. Yeah, I got the time. Thank you. I'll go faster as I get better at this. I already am starting to get more comfortable with this. Okay, and I think it's fine with the board here. We don't need it to be on the computer. So the computer is just for me. Anyway, back to it. All right, so where was I? Well, we're going to get to the net. So what I was saying is that the pyramid having all the lateral faces be triangles, that's really what gives it away. So when people are having trouble with the nets, I like to capture my base. I captured the base, right? And then everything else is a triangle. Like that. Okay? And these are the lateral faces. Lateral faces. Lateral faces. Okay? All right? And then, yeah, this is going to be every day. I see somebody's asking every day. Every day, just for an hour, though. Not on the weekends. Let's go to that last one. Triangular pyramid. Now I think you're getting the idea. So let's see. I'm going to draw that here. Remember, for the pyramids, you are stretching. You start with this base down here, and instead of pulling that up into a triangular prism, they're all, again, because it's going to be a pyramid, these points are going to converge into a point again. All right? So, and then if you look, the lateral faces are still triangles. So when you make your net, N-E-T, okay, you're going to have a triangle attached to each one. And I know some of you Zelda players are thinking Triforce, huh? There's your base right there. You guys know what Zelda is, right? Yeah. So there you go. So on a test, I'm going to give you one of these. And these are the ones that students mix up. You can see why. Let me see how that comes out. Maybe a side by side. I don't know. Like that. Yeah. This is what gets mixed up. All right. So you can see. Just look at that. Look at the base. All right. You know that these are pyramids just by looking at the nets because of all the lateral faces. Everything that's not a base is a lateral face. All of them are triangles. Automatically, I know it's a pyramid. So make sure that when you're being told on the test to do a pyramid, make sure that you capture that. All right, we're going to move on. All right, so here we go. Let's see what's next. Okay, so now we see if you can draw the net for, listen to this, a hexagonal, call it a no. Hexagonal prism. Hexagonal prism. See if you can draw a hexagonal prism and then draw the net for it. Hexagonal prism. Go ahead. When I say hexagonal, I'm telling you what the bases are. When I say prism, you know that there are two of them. That's right. That's right. 2 hexagons, 6 rectangles. Exactly. Now you got it. And if you're done with that early, I want you to start counting faces, edges, and vertices right now and see if Euler's formula still holds. Now, if you already saw me do this the other day, last week, please don't give it away. I really don't want you to put that up there. Okay? I appreciate your cooperation. All right, I'm going to start drawing it myself. I'm going to draw it as a polyhedron. Hedron is 3-dimensional, gon is 2-dimensional. I start with the hexagon. I start by actually drawing the base. Then I draw another one up above it. Try to get it to look about the same, or the same if I can. And then I connect the vertices. Sometimes these are hard to see spatially. There we go. No, I know, David. I know. Oh, you can see my computer? I thought everybody said they could not see the computer. Okay. Well, don't worry about the computer. We're doing this on the board. Okay, so now what I'm going to do is there's lots of different ways I can put this out here. But you can do it like I did the rectangular prism, is you can put out the 6 faces. Now, why would there be 6 lateral faces? Well, there's one for each side of the base, for each edge of the base. So now at this point, I can pick any one of these to place this on. Like that. And then down here, I could put it along any one. It does not have to be a cross. I just like to do it across so I can move on with my day. But if you want to play around with it and move that around, that's fine. So here are your bases. And then here are your lateral faces. Now, start counting those vertices, edges, and faces. I think edges there's always going to be more edges. Vertices, faces. So I'm going to start counting. You can start counting. Let me start with this one here. 1, 2, 3, 4, 5, 6, 7. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. I got 29 edges. A lot more edges now. Edges that used to be one, these two would have gone together. Maybe, you know, you're talking about here and here, right? Maybe that's the split, here and here. They would have imagined these being together. Okay, either swing the top towards you or away from you, doesn't matter. All right, so we gained a lot more edges from that. Vertices, let's start counting those. 1, 2, 3, 4, 5, 6, 7, what's up here? 8, 9, 10, 11, 12, 13, 14. Oh, is there a question? Oh, yeah, the net is a 2D figure. Yes. Yes, 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 yes. So let's see. 2, 4, 6, 8, 10, 12, 14, 15, 16, 17, 18, 19, 20, 21, 22 vertices. Now faces is the easiest to do. So there's the 6 plus the 2 makes 8. Now when you add up your vertices and your faces, 22 plus 8, you get 30. But the edges is 29. Something went wrong. Did we count wrong? The answer is no. Okay, so we did not count wrong. So something happened. We gained an extra edge in relation to the sum of the other two. We gained an extra edge. Okay, maybe it's when you broke apart one of these, one edge became 2, more than the other one split apart by 1. Now that you have one more edge compared to the others, you don't need that plus 2 anymore. You only need a plus 1. Yes, and I see somebody's putting up the formula now. So let's go to Euler's formula for nets. Okay, so we have Euler again. Thank you, Euler. Formula for nets. And that's going to be edges plus 1. And that's equal to the faces plus the vertices. Okay, so I could give you a problem, and one of the things you'd have to ask about the polyhedron is it three-dimensional or is it a net? And then that's how you would know. Let's see. Yeah, let's not ask about who's who, and let's avoid those comments, please. It's pretty disruptive. All right, I don't want to spend my time to teach if you guys are going to be focused on that. So let's get back to being focused here. Okay. It's really interesting enacting discipline over the internet. It's strange, but if it works, it works. Okay, so here we go. So if I were to give you the same type of problem I gave you before, where I could tell you there are, let's do it this way. Let's say that there are, in a polyhedron, there are 52 edges and 40 faces. I want how many vertices there are in 3 dimensions and as a net. Give me both of those answers, please. So we'll do 3D, 2D. We want how many vertices? Go ahead and do that, please. Okay, somebody said, why does this happen? It happens because when you split the sides apart, you gain an extra edge. What was once one edge shared between 2 faces, you still have 2 faces, but now you have 2 edges that used to be joined that are no longer joined. So if you look at my hands, if these are together and they wrap around to the other side, right, and I undo this, where there was a connection there and we counted that as one edge is now one edge over here and one edge over here. That's what happens. Okay. All right, let's see. Some of you are giving me the answers, the 3D. Okay, so let's see. In 3 dimensions, Euler's formula is this. Okay, so it's not, the math itself is simple. Are you going to remember the equations? Okay, because if I give this to you on a test, you're probably not going to draw a 52-edge, 40-face object. Okay, so this is going to be your way out, is to be able to do this. Okay, so in 3D, we're using the top one. 52 and 2 is going to add up to 54. Put a little 54 up there, so we don't have to hold that in our heads. With 40 faces, and you can fill that in. That's got to be a 14. 14 vertices. Okay, and then down here, same deal. You have 52 plus 1 is 53 with 40 faces. Okay, so you're going to need 13 vertices to achieve that. Okay, 14 and 13. All right, so those are not too bad. If you forget what Euler's formula is, what I would recommend you do is just draw, it's always true of all of them, so draw the one you know how to draw. Draw a rectangular prism and just calculate it out again. So that one is not too difficult to derive yourself. All right, so let's go ahead and clear our spaces and let's go to the next idea. And right now we're at 9:15. So we started at about 8:36, 8:35-ish. We don't have to be perfect, but definitely want to get to the end of at least one lesson. This one's almost done anyway. Okay, so we have that. Cross sections. Okay, this can get very interesting if we want it to. All right, so cross section. Let's take a cylinder. Okay, and let's draw a point here and a point there and a point here and a point here, and imagine that we took a metal sheet and slid it through to cut through this, and that would be a plane basically. Think of a plane cutting through this. Okay, and let's say it has like little handles on the side. Okay, and we're sawing it back and forth. Now you can pull the can apart, dip it in ink, and I don't want you to dip this part. I'm not talking about that part. Okay, I want you to dip the inside face. Now this new face that you have, after you pull them apart, you have to use your imagination now. And you pull it apart, dip it in ink, and stamp it on a piece of paper. And what shape are you going to see? There will be homework after some of these lessons, by the way. Yeah, it's going to be a rectangle. It's going to be a rectangle. So if you pull that apart and you do that, and so this is what we call a cross section. Here's what's interesting about cross sections. Cross sections, if you take the cross section of a 3-dimensional object, you're going to get a 2D object. Okay, so the 3-dimensional cylinder, you don't have to get something circular out of it just because it has circular components to it. All right, but it is going to be 2-dimensional. All right, now, what would happen if I took the cross section of a 2-dimensional figure? What do you think is going to happen? Take the cross section of, let's say, a triangle. What would that even mean, a cross section? How are you going to put a plane through it? Well, maybe you're not putting a plane through it. Maybe you're putting a line through it. Maybe you're getting this point, and you're only getting this layer of it. Maybe if you put the cross section here, this segment would be also like that segment, but it would be longer. Right? You're going to get different length segments out of that. Okay, but a segment is 1 dimension. And what happens if I take a cross section of 1 dimension? How do I do that? Here's a segment. Take a cross section. And then perpendicular to that maybe, or it doesn't even have to be. It could be cutting across. 2 lines intersect at exactly 1 point. That's the cross section right there. is a point. So you see, cross sections take you down. Yeah, exactly. Cross sections take you down a dimension. Now I wonder what would happen if you took the cross section of a point. That's pretty abstract. So that might be fun to think about that. Or what would a cross section of space-time be? I would say that a cross section of space-time would have to be a dimension down. It would be 3D without time. So it would be just like freezing, everything frozen, and that's one snapshot, one cross section of space-time would be just space. Okay? A wormhole, right? Maybe so, I don't know. But those would be fun to study or to think about. Okay? Anyway, cross sections. Now, cross sections could get pretty tricky, so let's see what we have for you there. One thing that I want to use cross sections for to get you guys to understand is that stretching of a base. Okay, so if I stretch everything up, right, and connect, all right. So basically, I took this base and I lifted everything up, straight up. I'm going to make a right prism here with this. And when I do that, you might think of a cross section as any part that I want to cut. I don't have to do this, but I can cut horizontally across this. Okay, this here is a cross section. Notice it's an isometry. It's a congruency transformation of the base. I move the base up. Okay, so it's identical to the base. So you could think of this as having a length, a width, and then the height would be how many of these layers stacked upon one another. All right, so this is what's going to build us formulas coming up, is understanding that those cross sections, what they could be. Okay, what about for a triangular prism? So I have one of those. So let's do on the other side here. So if I have this triangle here and another one over here, and these are identical, base 1, base 2. By the way, bases don't mean bottom necessarily. It could be front and back. It doesn't matter how you turn your object. And now I connect vertices. Okay. So it looks like a tent. Okay. So now I can have a cross section of this, right? What is cross section? It's just an isometry of the base. It could be if you cut down into this. Like that. There's a cross section right there, right in the middle. Okay? Does the cross section? No, it can be at angles. The cross sections can be at angles. We're going to do that in a little bit, and it's going to get difficult. Okay? Let's not use other people's names. And yes, exactly. Let's always cut down on the spamming. Unless you have a question, let's hold your comments. I like the questions. I really don't. We don't have room for all of the other stuff. It makes it hard for me actually to see when a question comes up. Does the CS always in the middle, the cross section? No. I could have done the cross section here. You're gonna see. I'm gonna have the warm up for 11.2 is going to be a cube, and we're going to try to make different 2D objects with different types of cross sections at different types of angles, and it gets difficult. CS is cross section. Okay, and all right. So what I want you to do is to draw a cube for me right now. Go ahead. I want to draw one too. All right, so I want you to draw a cross section that intersects the front and right faces of this cube. So here's the front face, front and right. Can you draw a cross section that will intersect both of those faces? Take a minute and see if you could do that. And I'll see what you guys are writing here. Okay, Mr. Face. Yeah, we don't. So we don't want the okay, Mr. Face. We don't want that. Don't put that stuff in there, please. And I really don't want to use names, so you know who you are. So please don't do that. It does not. No, it does not have to be parallel. So you can go at an angle. I mean, the warm up is going to start with this. Okay, it's going to start with this. I'm just giving you a simple one. So as a plane slides through, what is that going to look like when it comes into contact with each edge? Right? When a plane, the edge of the plane is a line or a segment, makes contact with another segment, it's going to make a point, isn't it? Start using some other colors here. So you might say that there's the plane coming in right there. Imagine a block, and this is, silly. Imagine a block of cheese. We're going to cut the cheese, everybody. Just, be careful here. We're going to cut the cheese straight down that line. And if we come straight, now you don't have to cut it straight down, but if you cut it straight down, it's going to eventually come out the bottom there. And I want this to look like it's in the background. So, okay. And then what's going to happen here is the knife comes through this face as you're cutting that cheese. Okay. Can the cross section be a plant? Yeah, a plane, I think you meant to say. Yes, it's a plane. Yes, we got it. We got the joke. Okay, so no, it does not have to be parallel to a face. This one goes diagonally. It is perpendicular to one of the bases, but I could have angled it. Could have angled it from one end and out the other end. I could have angled it to come out the left face and the back face. And that's what we're going to play with in the warm-up for the next lesson. Okay, and we probably will have time to end with that. So, any questions about this? I'm not seeing any. I think it's pretty straightforward. I think I'm going to go to the next slide. Okay, your favorite part. Here comes your favorite part. You know what that means. Homework assignment. Okay, here you go. So I would say that was a good orientation of, what we're going to be dealing with here. Okay, hopefully everybody can see this. Page 621, 2 through 28 even. You need to practice. You're going to need to practice. Okay? All right. But you know what? We're close to 9:30, and I'm thinking if the next one starts with the cross sections, then it's probably a good warm-up to go over for next time. So what do you think we draw this one to a close? All those in favor, say aye. We will turn this in when we get back. We will check the homework in each class. So just hold on to these. Whenever we get back, we don't know. However, you really do need to do these. You shouldn't be too busy today. Just go do it right now. The best time to do it is now. Okay? So go get this done. It's 14 problems that have to do with identifying faces and things like that. It should be real simple. Get it out of the way. Do not let this build up on you so that you have, 20 homework assignments to do the night before. Okay, just don't do that. When we get back, it's going to be review, test, review, test. You're not going to have time to be messing around with this stuff. So just get it done. You might even experiment by making different cross sections out of a cube so that you're more prepared. I'm going to be asking you, can you make a pentagon? Can you make a hexagon? Things like that. Okay. All right. So that being said, everybody stay safe. Wash your hands. I'm doing social distancing. I'm pretty much staying inside unless I have to. We're taking hikes outside, walks. Those are nice. Everybody else, we don't want to spread this. We want to be able to get back to normal as soon as we can, and it's going to really take a group effort from everybody. Try to pass that message along. I do miss my smartboard as much as this is fun and new. I can't wait to get back to the resources that we normally have the privilege of having. Um, Okay, so with that being said, let's get better next time at the not spamming. But you guys were pretty good, and be safe. And I'll see you tomorrow, same time, 8:30. We're gonna do 8:30 each time. All right. So I'll see you all tomorrow at 8:30, and I'm ending stream. Take care.